So, hello everyone. I'm here today to talk about what's up for Git and Java to JavaScript transpilation in general. For those of you who don't know me, my name is Daniel. I work at Google on the Git and nowadays on the J2CL team as well. If you want to hear more about Git and all these kinds of things, there's a chance to follow me on Twitter. With me today is one of my colleagues who also works on Git and J2CL at Google, Thomas Deegan. And he's going to give us a couple of demos on some really cool stuff. And first of all, let me say, we spent like the day yesterday going around Florence, and you have like one of the most beautiful cities I could ever imagine, with this rich architecture, these great buildings, and this huge cultural heritage. So we really enjoyed our day outside in the city yesterday. And we also want to give a huge thanks to the organizers of these conferences. Like most of the time when we go out, we have to organize conferences ourselves. So Google has to put in a lot of money and a lot of effort to make these things happen. GitCon is different in that way. I still remember like 2.5 years ago, when this whole idea came up of doing an Italian Git conference, and we just said, we were just surprised by all the organizers that put in all of the work to make that happen. We just had to come by and give a talk, which is way less work than organizing and putting together a conference. So we're really happy about this, and we're really glad to be here. So, if you want to ask any questions during the talk, if there's something unclear, I'll encourage you to do so during the talk. I don't want you sitting there for like 20 minutes thinking, what is he going on about? So if there's anything you want to ask, just interrupt us and we'll gladly answer questions. And probably you can throw a mic around for everybody to hear you. Let's get started. So today is going to be all about Java to JavaScript and what are the next steps for Java to JavaScript. But before we focus on the future, let's actually talk about the past. So you'll probably remember that back in 2006, web development was a really tough spot. There weren't any great web applications, like the first real Ajax applications like Gmail or Google Maps just have been released. Like most of the time the web was like, you clicked the form, you sent the form to the server, and you got a new HTML page. So there was no rich interactive web at the time. And certainly compiling from Java to JavaScript was not something that was usually done by people. Like I remember when we started Git, people were thinking it's a crazy idea. You would never compile Java to JavaScript. It just sounded outrageously stupid. But we did it anyway, and Git pioneered the whole idea. And if you look today, there's like basically any language now compiles to JavaScript and runs within the browser. And that's a huge achievement. That's partly due to Git making that idea popular. So today, if you want to run C++ code in the browser, you can use EM script. And if you want to run Dart code, TypeScript code, all of that stuff works. But if you think about the JavaScript ecosystem in 2006, there were basically no good JavaScript libraries. jQuery was just around the corner, but most of the JavaScript was just not good at all. So when Git started, we, for instance, didn't have JavaScript debuggers. So if you had a bug in your code, you literally were placing all these alert statements in there, and then you were trying to figure out where it's going wrong. That was completely unacceptable, because at the time, you already had a great Java debugger where you could step through, change your variables, and that kind of led to the idea, why don't we take all these great tools like IDE support and make them available for JavaScript development? At the time, it was also hard to do any refactorings in JavaScript. It's still hard today, by the way. So Git started off with this idea in 2006, let's just make developers productive. Let's reuse this large ecosystem of tools for writing web front ends that we already had on the server at the time. And the main idea was all developers should just be enabled to reuse the tools that they liked. But at the time, because there was no JavaScript ecosystem, interacting with JavaScript was just not a priority, right? All your program was written in Java, the compiler would take it and it would translate it to JavaScript. And that's kind of okay if there are no good JavaScript libraries out there. And that's what kind of shaped Git's future from 2006 on, becoming this full world optimizer. So all code would actually be running through Git. So all code would actually be running through Git. That's obviously really good for optimizing things, but it's not as great when it comes for interoping with JavaScript. So if there's other JavaScript in the page that the compiler does not know about, that's kind of problematic. But the idea of optimizing the full world has served as great. But things change, right? And eventually you end up in a different world. So Git is now legit over 10 years old. Like, I looked at the commit history, and the first commits that were basically not publicly were done in 2005. So we're like 11 years old, soon 12 years old. So that's pretty long time for a JavaScript or a web front end. And obviously the world around Git has changed, and these initial assumptions of we have this large Java program and Java is the language to use have changed, because if we look at this, there's all these other JavaScript libraries out there that bring like tremendous new ideas to the ecosystem. If you think about Angular, for instance, their data binding is just way better than anybody else's data binding. Or if you think about React, the ability to just update certain parts of the DOM and don't have to think about it, and just having a really fast library that does this. Or libraries like Polymer that pioneered new things like web components and made them really popular. Like before Polymer, nobody was considering that you could even use HTML as the proper language for your UI. Now we have all these great web components. So there's this huge other ecosystem evolving with these huge other ideas. And you could kind of ask the question, what about Java to JavaScript and its value? Why is it still valuable? Well, still all the old things that we used to have still apply. We still have Java as a great language. We still have really good IDEs. We have really good refactoring tools. Like if you just think about auto-completion in JavaScript, it's not there yet, right? There's a couple of attempts to do so, but it has nowhere near the sophistication we have in IntelliJ or in Eclipse. Also, if you think about code size and performance, we are much smaller. We're much more optimized than anything that is there in the JavaScript ecosystem. There's obviously solutions when you think about the Clojure compiler that can optimize annotated JavaScript well, but if you think just about the pure language, we're doing quite well there. And we haven't stood still. Like if you look at Java 8 and the Java 8 syntax, it's actually really terse. Like we always in the past got a lot of flack for being quite verbose with Java. That's not the case anymore with Java 8. And also there's obviously still lots and lots of Java developers. Like it depends on which numbers you trust, but most of the time the Java ecosystem is slightly larger than the JavaScript ecosystem, and we should enable these developers to write web frontends if they choose to write them in Java. But there's also a new aspect, and we do want new users to come to Git. And this new aspect is cross-platform. And I talked about this 2 years ago when we first publicly talked about Google Inbox, that we at Google believe that some applications can write really good cross-platform applications in Java and share most of their code. That's what Google Inbox is doing. That's what we're hoping that other applications will be doing as well. They kind of use Java as the common language. And obviously Java just runs fine on the server and it just runs fine on Android. So that kind of means you have to cover iOS and the web somehow. Well, the web you cover by compiling with Git. And iOS, we have a great compiler called J2 Objective-C, where you input your Java and you get back Objective-C code. But we also want other users to be interested in Java to JavaScript compilation. And these are the users that maybe have like 1 or 2 classes within their project that do like server-side validation, for instance. Let's assume you have a Polymer application that is mostly written in JavaScript, but you do server-side validation for all the models that come in. Why wouldn't you want to be able to take these validation logics and just compile them down to JavaScript and run them on the client as well to give your users faster feedback? Why would you want to write them 2 times? So this is obviously different from people that have chosen to use Java as their first language for writing all of their UI, but this should be a supported use case. This should not be hard, right? In the past, we've always forced people to do everything in Java. We don't want that anymore. And Git 2.8 is the first step in making this possible. And it has basically 2 core technologies built into it. And there is Interop, and we've been talking about that for a while, and then there's Elemental 2. So let's look at the actual GWT 2.0 release that we just published. And let's actually look at a couple of key things within the release. So I'll be talking about Interop, Java 8, GSS, and a couple of general improvements we've done with GWT 2.8. So Interop has this idea of, we have this other ecosystem of JavaScript there, and we have our Java code here. And they should be able to cross-call and use each other as they see needed. And it's quite important to understand that it's actually a two-way street. So you can consume any JavaScript. I'm having trouble seeing my slides, I'm sorry. You can consume any JavaScript library within Java, and that should be hassle-free. You could obviously do that in the past with JSON and JavaScript object, but it would require a lot of work and a lot of typing to do so. And you should be able to expose any Java code that you've written to JavaScript. This is not working great at all. So for instance, if I want to use jQuery, just a second. Any idea on how to make this visible?
Maybe mirror for now? Is that the best thing?
Yeah, maybe. The problem is, my slide preview is this big, I have no chance of reading the code. Oh, there it is. That's actually going to work. And I'm trying to read it over there, but then it's like inversed. That doesn't make it any easier. So let's say you want to use something like jQuery. And this is just for the sake of example. This could be any JavaScript library you want to use. And we actually have a couple of demos on how to do this. So you could be doing something like this. You could write a class, and the only special thing about this class is that it has an annotation on top of it that says @JSType is native true. So that means that the compiler understands that it does not have to emit any code for this class. This class is just purely a calling interface for JavaScript that is already in the page. And you know, when you write jQuery code, you write like $something, dot something, dot something. So what we do is we just add a static method, and we say this static method, we put an @JS method annotation on top of it. And that means this method is just in that global namespace, because we say namespace equals global. So every time the compiler sees a call in Java to that method, it's literally just going to emit $, for that method call. So that means we can now write something like this in Java. We can literally just say, give me all the list items of an unordered list, change that color to red, and set the data attribute. So this looks very, very familiar, right? This just looks like the JavaScript you would write if you wanted to use jQuery in JavaScript. But obviously, like, handwriting this interface is just a cumbersome job. Right? Nobody wants to do that. And this is where the Interop generator comes in. And I'm going to be talking about the details of the Interop generator in a minute. I first want to continue on the path on Interop. So let's just remind ourselves for now, there should be no handwriting of these interfaces. They should be all done automatically without you doing any extra work. The other thing that Interop enables is to expose Java to any JavaScript. Let's take again a very, very small example. Let's say we have a class called bar in the package foo. And this class has a Boolean field called bool. It has a constructor, and it has a method called foo that returns a string. So because I placed an @JSType on top of there, the compiler now knows, and it's not a native type, it knows it has to keep this type preserved. So that means it has to make sure that if I reference this type from pure JavaScript, that the names are not mangled. So they're not optimized and obfuscated anymore. Because it's in the package foo, we can now say new foo.bar, and this is just calling the Java constructor. And then we can say if bar.bool, which is just referencing the Boolean field on that class, we can then alert what's coming back from the method, and this would just alert hello GWTCon. So that's the main concept to understand about JS Interop. Consume any library that's out there, add JS type is native equals true, or expose any Java that you've written to JavaScript by just putting an @JS type on top of it. If you're interested in more details, I'll have an in-depth talk on all the different options you get this afternoon. You might want to see that. The next thing we've done in GWT 2.8 is Java 8. And you remember like callbacks in GWT, right? You've written that code and you hated that code, right? So in Java 7, if you wanted to have like a simple timer, you would do set timeout, you would write this anonymous interface, and within the interface you actually would put your code. So if you look at this is mostly boilerplate, right? It's really, really long. That's for instance, like IntelliJ has chosen to just render this as a lambda, even though you were writing Java 7 code. So this is how it looks in GWT 2.8. This is so much better, right? It's exactly the same thing, and there's not all this boilerplate going around. And the compiler will just make sure that this lambda you're using here, which is actually a Java type, ends up being transpiled as a function, so when you call Windows set timeout, it actually does the right thing. And obviously, you can do all kinds of callbacks. If you want to listen to a click event on a button, pass in a lambda, and it just works. But there's some other cool things in Java 8, right? We got streams in Java 8. And they're now part of the standard runtime in GWT as well. So we can do things like mylist.stream, .filter, so we can filter everything with a lambda that starts with a J. Then we can do to uppercase on these. We can sort them, and then we can output them to the console. Imagine you have to write this in a couple of for loops and somebody else has to understand what's going on. This is so much more terse, this is so much clearer. So this obviously alerts Java 6, 7, and 8. And it kind of leaves Dart out. But one of the reasons that people have chosen to use Java in the first place is Guava, like our standard Java libraries that we use within Google. And Guava 20 and GWT 2.8, we've made sure these work well together, and this is like the first release where we have all these proper Java 8 features enabled. So if you want to do something like building up a immutable list in Guava, and for the people who don't use Guava, immutable list is just a list that can't be changed, and immutable data types in itself have a value. There's collectors for all these kinds of things, so you can literally just take your list and import two immutable lists, and you can convert your stream into one of Guava's data collections. There's obviously much, much more to Java 8, but that's good enough for the keynote for now. Let me quickly talk about GSS. So the important thing to understand about GSS, at this point, we do not consider it experimental anymore. It's stable, and you should be using it. We're even going as fast as saying, no application at Google still uses the old CSS resource. We've migrated all of them to GSS, and so should you, because we consider the old CSS resource deprecated, and the next version of GWT might not have it anymore. But we did not turn it on by default. And the only reason we've not turned it on by default is to make migrations onto GWT 2.8 easier. So we did not want people to migrate all their GSS in order to be able to use GWT 2.8, but you should be migrating towards GWT 2.8, and as soon as you finish that migration, your next step should be move over to GSS. And there's a couple of big improvements there. If you think about code size, just changing everything from CSS to GSS will give you back like 1 or 2% in code size. We've seen that over Google's applications. And keep in mind, this is total code size of the application, and normally your CSS is not the biggest part of your application. So this is quite a big improvement if you only look at the CSS. And it will be much, much stricter. So if you actually do a type error, if you mistype, if you slightly use it wrong, it actually will blow up at compilation time, and it won't allow you to do mistakes in CSS at all. On the webpage, there's a guide on how to do these migrations. We've published a couple of tools that help along, so you all find all that kind of stuff on gwtproject.org. And let me urge this, this is now the time to migrate. If your application runs with Git 2.8, you should be doing that work now. Another thing we added is called system get property. And that's also new to Git 2.8, and it's kind of important because it enables migrations away from Git code generators towards Java annotation processors. Like in Git, when you wanted to access a configuration or a binding property, you would always have to either do all these long settings in your Git XML file, some of you might have done that, or you had to write an actual code generator that would access the values and emit different code. That was obviously a very tough job to do and a lot of work. So what we did instead is we just enabled you to use system get property within your program's code. And you could just ask for any variable value, and we guarantee that this is actually just an inlineable string. So this means if you're doing something like if system get property user agent equals Safari, and we're compiling the Safari permutation right now, this will just be true. So any code that is in there would either get stripped or it will be left in if you're in the right permutation. And you can actually set these values now directly from the command line of the compiler. So you don't need to go into your Git XML file and fiddle. You can just say -set property user agent equals Safari, and we will have changed that value. So a simple example. So you could define a custom variable. You could say define property, and in this case we're naming the thing foo.bar, and it has two different values, true or false. And we're setting the value to false. And then within my Java program, I could say something like true equals system get property.foo.bar. This will obviously return false, and thus the whole if condition will get stripped from your program. Another thing we added with Git 2.8 is the Git check system. For those of you who use Guava, you can think of it as being the preconditions in Guava, like check not null, and these kinds of things. But the main difference here is it's actually strippable. So this means that while you're developing, these checks are most of the time running, but for your production compiles, you can turn them off, and that will make your code faster and smaller. But you have to give up some amount of correctness in some cases. To make decisionals easier, we've kind of grouped them into different groups. And some of them are easier to disable, while some of them aren't. For instance, the first group is the bounds group. And these would be things like index out of bounds exception or raise store exception if you actually go out of the bounds of the array. If you think about JavaScript, in JavaScript nobody is checking for these at runtime, right? They're just setting stuff there. And if they set it to the wrong place, it ends up at the wrong place. So we give you an option to disable these. Then there's like API checks like null pointer exception, illegal argument exception, illegal state exception. And in some cases these are really important, but in most cases if you have correct code, they won't actually be triggered at runtime. So these checks are just causing you overhead. Then there's like things around types. If you cast from one type to another, you expect a class cast exception to happen, but if you've written proper code, these are never actually going to happen in production, right? And then there's critical checks. And the critical checks are checks that are important because if you misuse an API, the API is not going to blow up immediately, but it's going to do something really weird later on. For instance, if you break checks in an iterator, the iterator might iterate forever. So you're just going to end up in an endless loop. And to make it easier to use these, we kind of come up with different check levels. So the check level you normally get when you just compile with super dev mode or you do a production compile is normal. And all these checks are enabled. That's the default, that's the safe default. So your code behaves exactly the same like Java code is supposed to behave. But you can change it to optimal and you use the bounds checks and the API checks. So for instance, if you actually access a list out of bounds, it won't throw an exception anymore. It will just return null in that case. If you've written correct code, all your code works in development mode, your tests all work. This is a safe thing to do, but you have to be aware that there's some caveats to that, obviously. Then there's minimal. Some of our applications at Google actually run with minimal. They basically disable everything except the critical checks. And right now we've not enabled disabling the critical checks yet, just because we think the errors you would be getting are so hard to debug and so hard to understand that we don't want people to do this. Somebody could be making a good case for it in terms of runtime performance and code size, but we're not sure yet. Okay, I said this before, super dev mode always runs with the full checks. You can't disable them in super dev mode because while you're developing, if you do a mistake, we want the code to blow up in your face. But for your prod compiles, you can change it, and we've seen huge improvements in runtime performance. So for instance, if you set the checks to critical and you do iteration on a map, it can be 10 times as fast, just because we're not redoing all these checks on every iteration. It also gets rid of all these extra -x flags, like -x disable class metadata, disable class checking, because they're all now baked into these levels of checks, which makes that system much simpler. You don't have to pass like 10 different command line flags just to get these optimizations. And like with every GWT release, there's like major things we've done. I'm not going to go into details on this. I just want to quickly mention them. So we've made sure that, first of all, the compiler runs much faster. So there's an optimization framework in the compiler now that makes sure that only parts of the AST that have changed actually get rerun in the next parts. So let's say you've inlined a certain variable, only that specific part of the AST gets visited. That makes compiles much faster. We've changed the Java util maps implementation that we have to actually use ES6 maps if they're available in the browser that we run in, and that makes them run much faster. We've improved the runtime performance of long a lot. In some cases, longs are now even unboxed. They're just primitive doubles. So if you have a long that has a value of 1 and you have another long of 2, this is actually literally just 1 plus 2 in the browser now. Only if the long exceeds what you can actually represent in a normal double, which is like 52 bits, so you have to use quite big doubles, then we actually change back to like an actual object representation. But that's all done at runtime by the compiler. You don't have to care about it at all. Another nice one is double and boolean are now actually not boxed at all anymore. So even in your code, if you write new double or new boolean, we actually just have the primitive at all times. And how do you do this? Well, you statify all the calls to it. So all the code, when you write like something like new boolean dot boolean value, it's actually just replacing this with a static call, and the static call just returns the primitive. It gets inline. So literally, this would be var d equals true. This breaks a couple of use cases where people have passed like double and boolean uppercase into JSON, because they used to be objects and now they're primitives and they're called methods on them, so we banned them in JSON. So if you call any methods on double, number, or boolean in JSON, your compile will blow up in GWT 2.8. We felt that this was a safe thing to do because we scanned like through all GWT code that we can find, and we found like 2 occurrences of this. And they're easily fixable because if you know they're just the primitive, you can just pass the primitive and it's all fine. So one of the questions I always got for GWT 2.8, what did you guys do? Why did it take so long? Because it's been quite a while. So it's important to understand how we approach this. We figure that GWT 2.8 is a long-term support release. So it's something we want to support for the next couple of years and make sure it works well. So it meant it had to have all the important features, and one of them was Java 8 library support. This is what took contributors a long time to do and make sure that streams and all these things work properly. And we also wanted to have a stable JS Interop release that works well, that people can use to use modern features within their GWT applications. Because that kind of enables all the stepping stones, like Elemental and all the other stuff that is about to come. We're going to hear talks today about how we can use JS Interop to do Angular integrations. So we want to make sure that GWT 2.8 is ready for these kinds of things. And one of these core pieces that we need to wait on was Elemental. So Elemental has this idea of that if you have a type system somewhere, you should be able to generate JS Interop for that type system, right? And there are quite popular type systems out there for JavaScript. For instance, TypeScript. TypeScript has this huge repository of DTS files for almost any JavaScript library because they need that for autocompletion. And then there's Clojure, which is also a Google product, which is open source, which is a JavaScript to JavaScript compiler that we use in many products. And both of them, Clojure and TypeScript, can be input to the JS Interop generator, and it can just generate interop code for any of these. So if you have a DTS file for TypeScript, or if you have Clojure externs, we have a tool where you can feed them in, and you get lots of Java classes for that. So Elemental 2 is going to be a new browser API. So basically any browser API that you ever wanted to use, typed arrays, canvas, whatever, it's going to be there. And it's not created by hand like the old GUID DOM APIs that we used to have. It's actually generated from Clojure externs, which means if there's a new API, you literally have to add like a one-liner in the Clojure extern file, and all these APIs start appearing in your Java code. This also means that you get like nice auto-completion in Java for all browser APIs. And I can show that in a minute. That's actually really, really neat. The JS Interop generator will do that kind of type conversion. But it's not just bound to Elemental, it can do that for any type system. And that's the important bit. You want to use something like 2JS, which is a physics engine and a drawing thing for JavaScript, and Thomas will show that in a minute. You can just run the tool over their JavaScript, you get back the native types, and you can run them in the browser. So the idea is here, any JavaScript library that you think is good enough for you to run alongside your GUID code, we should enable that use case. And this obviously makes integration with Angular, Polymer, React, or whatever really easy, because you don't now have to handwrite all these types. You can generate most of the API that they're calling into, and maybe you do some extra code generation like Arnaud has done for Angular to make it easier to actually write code for that framework in Java. But most of the time, this should cover it through code generation. And I can't give you an open source version of the JS Interop generator right now. I can encourage you to try out Elemental. We've done a code drop of the generated Elemental sources a couple of weeks ago, and we're going to do another one really soon. So go out and check these out and give us feedback on these, because we're still looking at the generator and fitting with all the details on how you're supposed to output different types that are in JavaScript. But expect the JS Interop generator to be open source soon. So let's go through a simple example of how you could be using Elemental. So I have a simple class, and for the sake of the argument, we're not using an entry point here, we're just using a main method, because we're going to talk about another transpiler that can transpile this that doesn't know what an entry point is. And within that entry point, we're going to call a generated API and say, window at event listener, load. So when the page has loaded, execute this lambda and call the install method. Within the install method, we're going to create a button by saying document create element button, and we cast it to that specific type. Notice how we didn't do like different overloads here. Elemental is supposed to be bare down exactly to the metal, and we're not going to do any we're not going to put lipstick on the pig, essentially. This is what the browser API looks like, and we feel like we provide the bare API, and if people feel this is not a great API and there should be a create button element method, people can add that method on top of the base API. We'd always try to make these APIs better, but eventually this abstraction leaks into something else, and we feel that we should not be doing this anymore. So when we say button.textContent, set the text of the button, and we can add the button to the page. And this, except for the cast, looks like JavaScript, right? There's almost nothing. If you scratch the types, this is JavaScript you would be writing. Then we can say add a listener for a click event, and in there we can say remove the button from the page and do a window.alert. So this is what modern code looks like. A bare-bound API that just works out of the box. And let me give you a couple of guidelines. And again, we have a talk this afternoon that goes into more details. But if you write modern code in GUID, you're not going to be using any JSON. Every time you have this urge to write JSON, don't. JS Interop covers everything. That's not entirely true. There's a little bit that JS Interop can't do, but we're going to open source a small library called Base, which does basically a couple of things that you can't do in GUID with JS Interop with a couple of JSON lines. but it has a benefit of it will work going forward, even if there's no Disney anymore. Do not use JavaScript object. Do not refer to it, do not use it. You can use JS Interop to create something like a JavaScript object, and I'm going to go into details later this afternoon on how to do that, but there is no need for JavaScript object anymore. Do not use generators. So if you want to do code generation, don't use them. There's a couple of generators, obviously, like the GSS resource generator that you're using right now, and you can consider these being fine, because when you think about going forward, eventually somebody has to bring them forward to a more modern version. But if you're writing code yourself, don't use them. So what do you do instead? Well, you use JS Interop for interoping with JavaScript and doing all these kinds of things. You use Java annotation processors to generate code instead of GUID code generators. And you include the JavaScript frameworks that work for you and make your use case work really great. So that's modern code with GUID. So what does modern code look like with J2CL? Modern code in J2CL can do one thing that GUID can't do. And that means it can integrate with a Clojure compiler really, really well. So for those of you who don't know what the Clojure compiler is, the Clojure compiler is Google's JavaScript to JavaScript compiler. And it does so by adding type annotations to the JavaScript that we compile. So there's basically an extra type system sitting on top of JavaScript that the Clojure compiler understands, and it does optimizations based on that type system. So when you think about GUID, we always had this problem, like there's some Java and there's some JavaScript, and now they come together in the same page. And literally what you wanted is you wanted to optimize them together. But for GUID, that never really happened. And it did not need to happen for a long time, because for a long time it was fine to just write Java. But we're not coming to a point where we need to make sure that if we write a Polymer application, that all of our code actually gets optimized together. And if you have like one optimizer on the one side optimizing the Java and you have another one optimizing the JavaScript, there's still a lot of optimizations that don't happen, because you have to keep all of the public API between the two running. Or you have to feed everything through Clojure compiler, and then you have like all these problems on making it actually work. So let's move these apart. So the real solution here is to take something that processes your Java and turns that into JavaScript. And that exactly is what J2CL is doing. It's taking Java code and it's transpiling that on a per class basis to JavaScript. And it's not just transpiling it, it's also adding the Clojure type annotations, so that the Clojure compiler can look at this code and think it's actually been handwritten code by your user. It's not generated code at all. It just understands that code really well. Because then you can do this. You feed your JavaScript that you want to use into Clojure compiler, you feed your generated JavaScript into Clojure compiler, and you get this one optimized binary that contains everything. And all the bloat is stripped out just because the Clojure compiler is aware of everything. And this obviously enables sharing to a much, much higher degree than you can do in GUID. So again, I have a talk this afternoon where I go into details about these things. Go come see me. But for now I want to talk briefly about J2CL, or Jackal. So we call it Jackal internally. So it shares features with the GUID compiler, right? And it obviously has JS Interop, and I've talked about this before. It has Java 8 support. It actually uses the same Java standard library. So all the classes that you're used to, like Java util ArrayList, they're actually used by both compilers. Exactly the same. And Elemental works with both transpilers. So you can use it in GUID and you can use it in J2CL. But there's an important distinction. J2CL is not GUID 3.0. J2CL is a technology at Google that we work on. And GUID 3.0 will be defined by the steering committee, and Google is not in charge there. The steering committee is based on many companies, and the steering committee has to decide on how it treats J2CL. It could be possible that the steering committee goes ahead and says, well, J2CL is a really great technology, and we want to see this in GUID 3.0, and we'll build an SDK out of that. But for now, it's not open source yet, right? So this decision can only happen once we can actually throw it over the fence. So what does it actually do? It takes a Java class and transpiles that to an ES6 class. It doesn't do any optimization. You can think of it a little bit like TypeScript. When you write in TypeScript, you can see what kind of JavaScript it's outputting. We could do the same thing with J2CL. You type and you see on the other side what kind of JavaScript is outcoming there. Ooh. And then all the optimizations, we've moved them onto Clojure Compiler. So we spent a lot of time on making Clojure Compiler better and making it really good at understanding type systems, so it could do all the same optimizations that Gwt did in the past. And code generation is not something that runs within the compiler anymore. It's something that you do before you start to compile. So if you want to generate code, you could do this with any tool, or you can use a Java annotation processor. And for J2CL, all generated code is just normal source code. There's nothing special about it. You feed it through the compiler and it just transpiles. So if you think about things like Google Auto or Dagger, they're just generating code with Java annotation processors. J2CL can just translate that code. There's nothing magical about it. So it's source to source transpiled. To be clear, it's Java 8 and modern features to ES6. So the output is not directly runnable in IE8, but it runs directly in Chrome, Firefox, and any modern browser. If you want to run that output in IE8, you would need to invoke the Clojure compiler, and the Clojure compiler has a setting where you can say, my input is ES6, but I want ES3 code, so it takes all of your nice ES6 code and transpiles that to really old JavaScript. It's not as readable, but it works in an old browser. And because of that, we decided to, because this feature exists, so we decided to just do modern stuff, and eventually nobody will care about the old stuff at all. And it's blazingly fast because it's not doing all these extra things that Gwt used to do. So let's take a simple example. Let's take this class that has two methods, one static method and a normal method. So we have like one method called message, and it returns a string, and then we have the static method getMessage, and it returns a string that is built up of a constant string and an invocation of the constructor and then a method. So how would this transpile down to an ES6 class with J2CL? Well, first of all, you have to create the ES6 class, and that's just the class literal in the class keyword in JavaScript as well. Then you have to say it extends Java-lang object. There's a bug in some browsers when you just say extends object that it sometimes confuses that with the built-in object, so we renamed Java-lang object just to be on the safe side. Like normally these classes are not renamed, but object is kind of a special case. So we take the method and we transpile the method, right? And this is what comes out. ES6 classes are pretty similar to Java classes, but we also add type annotations on top of there. So we add the Clojure type annotation, say, well, this method is public, and it returns a nullable string. So the string could be null or a string. Then we transpile the static method. We add the type annotations here on top. Note how this is just invoking the normal JavaScript constructor and then calling the method in there. It's very similar to the Java. And then in Java, this was implicit. We had like a constructor that was calling the superconstructor. So in JavaScript, we have to do the same thing. And we add the type annotations for that as well. If we feed this into the Clojure compiler and just alert what the getMessage method will return here, it will literally inline this to alert the string. So why is Jackal not open source yet? Why aren't I demoing this and you guys are all using it? Well, as I said before, it's an experimental technology. And with new technologies, we're always changing things rapidly. So you, as a user that is not within Google, you're not going to have a great time because we're breaking things and we're trying to make the best thing we could possibly do. Once this gets more stable and we feel comfortable about it, yes, we're going to open source. We're committed to open sourcing this. Also, the open source story is very different from how we run things internally. You may know like Google has its own build system and its own set of tools, so how we drive that transpiler internally is very different from how you develop code. Like somebody needs to build an Eclipse integration, an IntelliJ integration, a Maven integration, and it's just things we're not doing right now. Because right now we're focused on internal customers. We want to get like important internal customers to really, really like J2CL because that makes sure that we have a long-term funding and a long-term mission to make it really good. But make no mistakes, we're going to open source this. So just to give you a little bit of an idea who's actually using J2CL, well, Google Inbox used to be this cross-platform application that we talked about 2 years ago is migrating from Git to J2CL right now. But we also have another big one, which is Google Docs and Slides, which is investigating moving onto J2CL, and it's already running for a limited set of users right now. So if you're in a certain test group, you could actually be looking at a J2CL integrated Docs version right now. And obviously, if you think about something like Google Docs, this is a word processor that is downloaded every time you open up a Google Doc, right? So this is critical in terms of runtime and especially code size. So we were not allowed to regress their code size at all. So that's why we spend a lot of time making sure that J2CL is better than Git when it comes to code size. So this is taking the Box 2D benchmark, and we've done this a lot of times in the past where we've transpiled this from different languages, and it compiles it down with different optimizers. So there's a Dart version, there's a Word version, and so on and so forth. So if you look at this, let's leave the really big ones out front, like if you compile from C++ with EM scripting, you're going to have great performance and runtime, but you have a horrible code size. So let's look at the group where we kind of have the same kind of languages. So let's take the Git version as the benchmark at roughly 100K. So you can see like Dart compared to that is 50% bigger. But with J2CL, because we've spent so much time putting work into the Clojure compiler, we're actually coming out smaller than Git used to come out. And I'm really proud of that work. Because code size and runtime performance are such an important thing. Is it? Ooh. Okay, that's better. So code size is such an important thing. So every time your user opens your web application, it has to re-download. So there's waiting time. And for applications, you all know this, like the faster a big website is with ads in there, the more revenue you're going to have. But it's not just about the download time, the parsing time that you have to redo every time. It's also about optimizations. So if you look at a modern JIT like V8 or the JavaScript engine in Firefox, they optimize differently depending on the code size because they have to do fast decisions. When they look at a method, they have to say, well, does it make sense to inline that method? And they can't really look at all of the AST and make that decision. So V8, for instance, just looks at the code size of a method and says, well, is this worth inlining or optimizing? So if you have large symbols in there, a method that might have got optimized if these symbols were smaller might not get optimized if these were bigger. So this is really important, and if you're doing development in JavaScript, make sure you're doing these things properly. So now it's demo time. I think I have to set this to a lower resolution though. Is this readable? Does it look okay? So let's start off with a very simple thing. So I talked about auto-completion and elemental, right? So I have elemental in my class path here, so I can just trigger auto-completion and say, well, I need an HTML button element, right? And I can do something like equals document dot create element button, right? So this is basically the same code you would be writing in JavaScript. The only difference is I actually get proper auto-completion. Because we're in Java, we have to adhere to the type system, so we actually have to cast this. When it comes to casting and native JS types, the compiler in this case will actually insert that this thing actually has the proper instance of call. You can turn them off if you want to, but this is actually not a no-op. So if you try to cast, let's say, a div to a button, it will actually blow up. So next we could be saying like button dot, and I would be saying all these things I could do on a button, right? So in this case, we just want to say text content equals click me. And then let's add that button to the page. So I can just be saying document dot body dot append child and put in, the button. So and now if I go to my browser, this one, it recompiles and there's our button. Let's make this slightly more interesting. So we can say button at event listener. We want to have a click event here. So we're going to use a Java 8 Lambda, and we're just going to say sorry. So we're just going to remove the button from the page. And then we're just going to say window.alert. So let's recompile that, press the button, and it's gone. So that's what Elemental is. A direct browser API for all these things you could possibly be doing. Let's do a second example. So you could like draw on an HTML canvas, right? And in Elemental, there's obviously an HTML canvas element. So we're going to just create a canvas here. Obviously, we have to do the cast again. That's just how the browser API works, and we've chosen to not pave over that detail. You actually have to do these. So then with a canvas, you want to say set the width. So we're going to say like 520 pixels this way. Height, right? So now we have a canvas in the page. So we're going to go canvas, give me the drawing context. So I get the 2D context of that canvas. Just going to call that object for now. And then I have like a library in this thing that can actually draw stuff on the canvas that I can just use. In this case, we'll use ray tracer. Let's just do Okay, this looks good to me. So all this is doing is creating a canvas, setting it to a certain size, and then asking Ray Tracer to draw a scene on it. So we recompile this, and it takes a while because it's actually now doing the 3D rendering, and then once it's done with the rendering, it's actually going to start drawing in 1, 2, 3 now, and there it is. So basically put two JavaScript libraries together and draw anything on a canvas you wanted to. Want to go next?
Sure.
I just have like a fun little demo that shows off some of the power and flexibility of this new JS Interop generator. So all the sort of type completion you just saw in Eclipse here, those Java facades, those calling interfaces were generated by the JS Interop generator. Those weren't handwritten. So someone took typed definitions and put them through the JS Interop generator and generated these Java calling interfaces. So that's what you were seeing in this demo before. So now I'm gonna take to let's say so I'm gonna take this to JS. Let's see if we can find it. So there's this two-dimensional drawing library. They have some great drawing technology. They can draw with WebGL and then with SVG if you don't have WebGL available in your browser. And they have some APIs for drawing circles and stuff like that. So if we look to the source, they already have these typed definitions published. So these are the externs published for the Clojure compiler. So if somebody was writing in JavaScript and they annotate their code and they pass in this extern file, the Clojure compiler will type check their code and optimize it very well for this library. So we're going to demo using this extern file passed through the JS Interop generator, and we're going to interface with this to.js library through this JS Interop interface. And so just a little more detail about the Clojure type system. It's actually quite similar to Java in a lot of ways, which is nice, convenient for us. They have generics, they have inheritance, they have polymorphism. So mapping it to Java is easier than expected, I guess. So we're going to demo using this drawing library, and then we're going to pull in the JBox2D. Right, so there's, someone's ported the C++ Box2D engine. So this is just a physics engine. And so what I kind of want to demo is how easy it is to interoperate now with, we're pulling in JavaScript and we're pulling in Java, and we can just kind of use them seamlessly together. And so I already have the code written. I'm not going to do as much coding as Dan did. And I actually have it running on a different machine because this is actually using Jackal. But nothing that I'm doing right now can't be done with Git. So, let's see if we can look at the sort of well, I wanted to find the kind of the intro that they were basing this off of, but as you can see, we're calling types from this to.js library, which are pulled in from this extern file. So this two constructor params, these are the parameters you pass to the constructor of the to.js library. And those kind of invoke and start up the rendering library. And so these types were generated, and we're calling them here. And so let's just load up the demo real quick. So yeah, fancy, let's get some bouncing going. And so if we wanted to, we could, maybe make, I don't know. Let's just leave it at that. But if we look at this code, so we're using here we're calling into this native JavaScript library in this code, and then here we're calling into this Java library, and they just kind of seamlessly interact here. And then here we're using Java 8 and we're using the browser API again, which is generated with the JS Interop generator. I guess the rest of the code isn't that important, but what we wanted to demo is how seamlessly now you can pull in JavaScript libraries and kind of the target, what we want to push this Java to JavaScript transpilation. We want to allow in Java for you to kind of with minimal effort to be able to generate these Java facades to JavaScript and be able to call, frameworks. Maybe you need some code generation for Angular or some of these other frameworks with lots of dynamic concepts. But in Java, we want to give you access to all these amazing, modern JavaScript libraries straight from your Java code. And then on the JavaScript side, we want to push the ability for people to say, okay, I'm writing a JavaScript app, but I want to write some of my code in a typed language, and I want to share that code between my server, my Android application, my web application, and then you can transpile to iPhone 2 with J2 Objective-C. So that's kind of our vision going forward, and I guess we added more balls.
I think you need to shift a little bit.
Anyways, yeah. So that was my demo. So kind of just pulling in JavaScript libraries and using them seamlessly with Java libraries at the same time. Yeah. And so obviously, here we used an extern, which is a sort of a typed interface to this JavaScript library. But we could, if this library was well typed so in this case, you would want to pull in that library separately. You wouldn't compile it with your code, and maybe you would download it from a CDN, so maybe it's cached pretty often. But if this was a well-typed library and had closure externs, or it had closure annotations in there already, we could compile it in with our Java code, and it would optimize very tightly and produce very small code, which is something we want. And I guess so this demo uses the closure externs, but we also have the TypeScript definitions coming in too. So there's a pretty big repository out there for almost every library you can think of in TypeScript. So we'll be supporting that too. Yeah. Yeah, so that's it.
So let's get back to slides. This is actually going to fill up all on my screen. But just keep it running. Yeah, I better close this off then. That's the wrong one. So today we've basically given you an idea of what Google thinks about Java to JavaScript transpilation going forward. That we think that we're going to see a more diverse ecosystem where you have to mix certain parts when you want to write good web applications, and that we want to provide the tools for making that mixing really easy. I think we're pretty excited about where we are right now. And I think you hopefully share that kind of vision that we got here, like how we want to enable Java to do really great web applications. And we don't want to fence ourselves off from the rest of the community. We want to make sure that we are well integrated and that people can even write libraries in Java and expose them to JavaScript developers, and these JavaScript developers can just use them. That's the eventual goal that we have. So first of all, let me thank you for coming to this and listening to our talk.